Good morning. My name is David Pridmore, and I'm presenting Reducing Furnace Operating Cost, How IGBT MFDC Technology Saves Energy. I'm presenting today from Roman Manufacturing, located in Grand Rapids, Michigan. We specialize in water-cooled transformers and power supplies. Our company's been in operation since 1980. We've sold over 1 million transformers. We have standard product offerings for the furnace industry. We also specialize in component and system sales. We're excited to introduce our IGBT MFDC power supply. The IGBT portion stands for Insulated Gate Bipolar Transistor. That's the control portion. MFDC stands for Mid-Frequency Direct Current. That's the high current transformer portion of the power control. This is used to replace SCR and VRT power controls. Some of the benefits that IGBT MFDC offers is less kilowatt usage, lower peak demand, and better power factor when compared to these other power controls. In this presentation, we're going to go over a case study for an IGBT MFDC retrofit of a VRT furnace. In this case study, we will demonstrate a 40% reduction in kilowatts, a 14% reduction in peak demand, high displacement power factor, which correlates to lower costs, and a savings of over $28,000 for a single furnace. Here you can see the details to our retrofit. On the left here, we have the VRT and vacuum furnace as it was originally. The VRT was rated at 645 kVA and had approximately 20-foot long water-cooled cables that went from the VRT to the power feed-through on top of the furnace. It took approximately 1 week to remove the VRT and place our IGBT MFDC system, which you can see here on the right. A couple things I want to point out here. One is the MFDC transformers are located on top of the furnace near the power feed-throughs. This is an important part of our value proposition that I'll get into later, but take note of that. So in general, we did a very good comparison of a VRT to an IGBT MFDC power control, as most elements in this retrofit didn't change. We used the same furnace, the same heating elements, so it was really a good comparison of how our power characteristics compared to the VRT. In order to compare the two power supplies, we ran the same cycle with the VRT in place, and then ran that same cycle again with the IGBT MFDC power supply in place. You can see from our heat treat cycle here that we ran at a ramp rate of 10 degrees Fahrenheit a minute up to a soak phase of approximately 1900 degrees Fahrenheit. We then measured upstream three-phase power, essentially what the power company sees, at the main breaker that went directly to the heating power supply. We then characterized these two phases of operation. We looked at the ramp rate, and then we looked at the soak phase. Before I get into the results of our case study, I wanted to go over some basic definitions of power. So real power, or kilowatts, is our usable electricity. Reactive power, or kVAR, is our wasted electricity. On the right here, you can see our power triangle, where real power on the bottom is 90 degrees out of phase from our reactive power, or kVAR on the right. The angle that this forms is known as the displacement power factor. I'll go into this more later, but it's essentially how the current can lead or lag from the applied voltage. There are three components that we're looking at during our experiment here. One is the total kW hours, which is a billable quantity, the peak demand, which is the most amount of current drawn, which also has penalties associated with it, as well as this displacement power factor, how much that current can lead or lag can make energy more expensive. Here are the results for our case study. First, let's look at kilowatts. The graph here shows the comparison of kilowatt usage of the VRT versus our IGBT MFDC power supply. Let's break down this graph here. On the left, the y-axis is real power measured in kilowatts. And on the right, we have a secondary y-axis that shows temperature in degrees Fahrenheit. This is what was shown on the previous slide, where we ramp up to a 1900 degree soak phase. The two lines represent the kilowatt usage of the VRT and IGBT MFDC power supply. And this trend is kind of expected when you think about it. As the furnace is ramping up in temperature, it's going to take more energy, and at higher rates, the hotter you get. And then when we get to our soak phase, we drop down into a plateau because we're simply maintaining a heat. We identified a 40% reduction in total real power consumption, or kilowatts, when comparing the two cycles. Next, let's look at the peak demand, or the most amount of current that's used for the process. This graph is similar to the last slide, where you have the heat treat cycle in blue and a plateau up to 1900 degrees, but our left y-axis now is amps, or current. And again, you can see the trend of increasing current during the ramp phase and then a plateau phase. In the circles in the graph, you can see our peak current draw. And we identified a 14% reduction from the VRT to the IGBT MFDC power supply. This correlates to lower peak demand charges for the furnace, and you can imagine a cumulative reduction the more of these controls you have in your facility. This also offers you the ability to change your ramp rate. You can get up to heat faster for the same rate and be more productive, or you can focus on the peak demand, really drop that down in your facility. And the reason why we see a lower peak demand is that our control, which I'll get into later, we rectify the three-phase 480 volts upstream to 650 volts out of the control into the transformer. That higher starting voltage allows us to step down that voltage further in the transformer, and that results in a lower primary current draw, which you see throughout the entire system. And finally, let's look at our displacement power factor. This graph is similar to the previous two, but on our left y-axis, we're looking at displacement power factor. Now, a good displacement power factor is close to 1. That means power is being delivered most efficiently to your system. As a power factor gets lower, it can incur penalties in your system or other issues. And this is why some customers will use capacitor banks at their facility. You can see with our IGBT MFDC power supply, our power factor remains near unity throughout the entire cycle. If you were to compare this to phase angle control, as the power drops down and we go to a lower set point, you would see a lower power factor, let's say in this plateau phase, because power is being delivered inefficiently. One thing I want to point out too is that we matched our system to the 645 kVA VRT. During this cycle, our system never exceeded 300 kVA. So at its maximum point, it was still 48% of the total capacity of our IGBT MFDC power supply. And even at these lower set points, it was lower than that. The take-home point is that our power supply has a very good displacement power factor at practically any set point. In this slide, we're going to look at kilowatt usage more closely. So these graphs are similar to the first graph I showed you, where the left y-axis is kilowatt usage, and the x-axis on the bottom is total time. If you integrate the kilowatts used over time, you get to the billable quantity of kilowatt hours. So the difference between the VRT and the IGBT MFDC system is approximately 194 kilowatt hours. That equates to a savings of 38 kilowatts per hour of use for this furnace. If you use the furnace for 20 hours a day over the course of a year, you could realize savings of up to $28,000 from kilowatt savings alone. This doesn't even take into account some of the other factors that could improve savings, such as power factor improvement, lower peak demand, and decreased weight. And ramp rate adjustments can be made for more productivity because we can get up to heat faster for the same cost. How does this all work? Here we have an IGBT MFDC schematic. Let's start on the left side. Our input into the system is 3-phase 60 Hz AC. We use 480 volts here, but other nominal voltages can be used. Within the control, we first rectify that 3-phase into DC 650 volts. This is smoothed over a capacitor and then inverted with IGBTs into high frequency, low current output. This 650 volts at 1000 Hertz is delivered to our MFDC transformer and stepped down to low voltage, high current. Within the MFDC transformer, we have diodes that then rectify that high frequency AC waveform into a low DC voltage, high current output. That DC current is then delivered to the load or whatever heating process you're using. Now let's get into some of the theory of why this is so much more efficient. Let's start with our first point, which is DC output is better. With DC output, there's no inductive reactance. If we look at the triangles here, on the left we have Ohm's law, described visually, and on the right we have our impedance triangle. So with AC output, we not only have the resistance of the circuit, but also the reactance, which is a function of the AC waveform and the area of which that secondary circuit contains. AC has more resistance in the form of impedance because you have more of that inductive reactance. By using DC output, we reduce the resistance or impedance of the system, and that means less energy is being subtracted away outside of your hot zone. This also goes back to our initial description of close coupling of our MFDC transformers to the power feed-throughs on the furnace. That very short secondary circuit also reduces resistance, which reduces unnecessary losses outside of your heating zone. On to our second point, our system uses shortened secondary cables. I touched on this on the last slide, but I want to go into the physics of it more here in this slide. On the left, you can see Joule's law, which shows heat is exponentially proportional to current and directly proportional to resistance. And by Ohm's law, we know that current and resistance are indirectly proportional to each other. So if we can reduce resistance, we can increase the current through the heating elements, which makes heating more efficient. By reducing the length of the secondary cables, we have less losses or less resistance getting to those power feed-throughs. Our third source of efficiency is inductive shielding. So what is inductive shielding? The graphic here shows how current can lead or lag from the application of voltage, depending on how much capacitance or inductance you have in the system. An ideal power factor is when the current waveform is directly over the voltage waveform, and that would correlate to a displacement power factor of near unity. Effectively, with our IGBT MFDC control, with the rectification, the capacitance, and the inversion, we shield that highly inductive secondary load on the heating element side from the power company. So we see a power factor of near unity at any set point. Our fourth source of efficiency for our IGBT MFDC system is the DC heating pattern. So simply put, the DC heating pattern is better than the AC heating pattern. The graph here shows on the left that the heating pattern of alternating current changes from 0 to its maximum during each half cycle of the frequency. This reduces the quality of the heat due to the large variance in instantaneous current to the process. The DC waveform here, shown on the right, delivers more stable heat. In conclusion, and as a summary for this presentation, we have demonstrated a retrofit of a VRT vacuum furnace with our IGBT MFDC power supply. We observed a 40% lower power consumption in kilowatts, a 14% lower peak demand, and a displacement power factor of near unity across the entire cycle. This correlates to real cost savings for furnace applications. Some of the other things that I didn't touch on in the presentation are that there are other forms of savings with using our IGBT MFDC system, which are decreased size of breakers, feed wires, and distribution transformers in your facility. Thank you very much for joining me today. You can find us at www.romanmfg.com.